In this lecture, we're gonna talk about quality assurance and calibration methods. Now, the purpose for this particular chapter is to help you understand how you make a choice of the best analytical method to use. Now remember, there are many analytical methods out there, and often as an analytical chemist, you are required, to think of what is the best analytical method to use for an intended purpose. So how do you go about, choosing between so many different analytical methods, and how do you determine which is the best one, to use for a certain type of purpose? And so the learning outcomes for this chapter is for you to be able to demonstrate a good understanding of the factors that determine how you make a comparative evaluation between different analytical methods, and how you go about arriving at the most appropriate analytical method for an intended purpose. Now, also very important is for you to gain a qualitative and quantitative proficiency or competency on different types of calibration methods that I'm gonna cover later in the chapter. Now, factors at play when you're considering what analytical method to use would be things like, the cost of the purchase of an instrumentation. Now, different analytical instrumentations, have got varied cost prices. For example, an AAS, a graphite furnace AAS, for example, is probably around $30,000 more expensive than a flame atomic absorption spectrometer. Now, an AAS, atomic absorption spectrometer, for example, is about $100,000 cheaper than an inductively coupled plasma optical emission spectrometer. And both of those spectroscopic techniques, do very similar things, so the cost implications are very different, so the budget is important. Now, the cost of operation also very important. If you compare an AAS, to an ICP, the ICP is much, much more expensive to operate compared to an AAS. Also, the technical expertise required, for example, for a mass spectrometer is much higher, compared to a typical emission spectrometers, spectrometers. Other implications or things that you need to consider are sample throughputs. If you take a look at, say, an ICP compared to an AAS, an ICP you can run 70 elements in a single sample all at the same time. With an AAS, you have to analyze one single element at any given time. So if at all you are in a high throughput lab, meaning you're getting probably 1,000 samples a day, and you need to profile all the different elements, maybe in a water sample, lead, mercury, and so on, you're probably, gonna look at an ICP because it can handle so many samples to analyze so many analytes in a single sample, in a single sample very quickly. So sample throughput, which means the number of samples I can run in a specific amount of time, is very important, when you're choosing an analytical method of choice. Things like portability, do you want to take, the instrumentation to the field, or do you just want it, on a lab bench? If at all it's a lab bench, then it doesn't have to be that portable. It can be the conventional bulky instruments. Also, the space footprint, do you have a big lab, and so space is not a problem? At all you're working with a very small lab space, then you have to consider which instrumentation, have got a smaller space footprint. Even things like power consumption. When you're thinking of portable instruments, you don't want to carry a big battery with you. That adds to the bulk. It also costs money depending on how much power a particular instrumentation is consuming. So that's another important consideration. But the focus for my lecture today is for us to look at the analytical performance indicators that you need to think about when you are trying to make a choice or comparing different analytical methods and trying to make a choice, out of those. And that's what I'm referring to as the figures of merit, or what you call the analytical performance indicators. Now, the figures of merit, as I've said, is a criteria of indicators that quantitatively compare one analytical method to another. And as you're going to realize that these figures of merit that I'm going to enumerate in the next slide can most often be obtained, from the calibration plot. And so you're going to find the importance of calibration plot, not only, to quantify or to determine the concentration of what you're looking for, but also as a way to extract the performance indicators that enveloped in a calibration plot. So very important. The figure of merit, most of the figure of merit indicators, you can get them from the calibration plot. So very important, calibration plot. Now remember, the whole intent of a calibration plot is to be able to develop a model or a relationship between the instrument signal and really what you're interested in, which is concentration, of a chemical species in a sample. So really you want the signal from the instrument, which can be absorbance, if at all you're doing spectrophotometry. It could be intensity, if at all you're doing something like emission spectroscopy. It can be voltage, if at all you're dealing with potentiometry. It can be current, if at all you're dealing with amperometry, and so forth. Or it can be simply arbitral units, if at all you're dealing with something like fluorescence. And all those signals should be proportional to the concentration. So that's what you're looking for in a calibration. Now remember, this relationship, ideally, it should be linear. So the calibration plots, in general, you should be getting a linear relationship, which means if I increase the concentration of my analyte, then the signal should increase in the same magnitude. And that's what we are looking at, in a linear calibration plot. Maybe I give you an example, using a lab that you guys are gonna do in your experiment 2, which will be detecting or analyzing trace amounts of iron in a given sample using spectrophotometry. That's gonna be your first lab that first real lab that you're gonna work on. Now, as you do the labs, I emphasize the importance of you, not only, of course, getting the hands-on experience, but also understanding the chemistry at play, in that particular lab. So it's important, for you to read the introduction and understand, the chemistry, that is at play, in that particular lab. For example, in your spectrophotometry lab where you're detecting iron in a sample, these are the two reactions, that you'll be engaging. So you'll take a sample that contains iron. Now, iron, remember, exists in two oxidation states. It can exist as iron 3+, it can exist in iron 2+. Ideally, you want to convert all the oxidation states present, into one oxidation state. And so that's what you do here, and that's what you're gonna do tomorrow. You take your sample, and then you're gonna react it, with hydroxylamine, which is a reducing agent. so that any ion in a 3+ state is converted, to the 2+ state. After you get, the ion, with the oxidation state of 2+, now you can react it, with a chromophore that you refer to as bipyridine, to form an ion bipyridine complex. It's important to remember the type of chemistry, that this is. And this is what you call complexometric type of chemistry. And later on, I'm going to highlight different types of chemistries in form of their equilibria, which you guys sort of covered in Chem 1 or 2. But I'm going to remind you again, So this one is complexometric type of equilibria, where you've got your ion reacting with the ligands, that are present in the bipyridine. And you can see the ligands, are these nitrogens, that have got a lone pair of electrons. And so the bond that is formed between the ion center, and the N or the nitrogen, is what you call the coordinate dative bond. I wanted you guys to answer that question. But nonetheless, it's a coordinate dative bond, because the electrons that are involved in the bond formation are all of them being donated, by the bipyridine, and, the ion is just receiving them. Now, it's important to remember, when you're doing quantitative analysis, any reaction you perform, needs to happen quickly, so the rate of that reaction needs to be very, very fast. And, you should be able to get, a complete transformation. And that's what we are referring to as the KF here. So in general, the KF, which is what you call the formation constant, it needs to be fairly large. And it is in this, reaction. Maybe as a homework, why don't you look in the literature, at the magnitude of the formation constant, between the ion 2+ and the bipyridine. Also remember, very important, for the stoichiometry to be known and to be balanced. So make sure you balance, your reaction, which it is right there. But back to the focus, of our, chapter here about the calibration, So you're gonna make the calibration standards, the standard solutions, meaning the concentrations of those standard solutions are very, very well known. And so you're gonna create, a standard solution of 0.0002 moles per liter, of the iron. And you make a dilution and you analyze using spectrophotometry, all the different absorbances of your different concentrated standards, okay? And you get a data, that looks like that. Of course, you're going to take your unknown. You don't know its concentration, but when you run it on the spectrophotometer, you're going to know its absorbance. And so the question is, how do you determine the concentration of the unknown now that you know the absorbance or the signal? And so that's the purpose of the calibration. You plot the calibration using your calibration standards. So these ones are known, so the concentration, you plot it in the x-axis, and the signal, you plot it in the y-axis. Now you generate the regression model, which you can easily do using the Excel spreadsheet. And I'd like you guys to familiarize yourself with the functions in an Excel spreadsheet. And just to mention that I've shared with you a generic template, that you can use and modify to suit the problem in question. So remember, the template that I've shared with you is only to help you guys get started, on how to use Excel, to do your calibrations. So you generate the linear regression. And based on the linear regression, the y is equals to the slope, x, plus, the intercept. And now you can calculate, the concentration of the unknown using this regression. Remember, what you're looking for is the x. You already know the y. The y is a signal. And so you can substitute, the signal here, the 0.44. and then determine the X, which is a concentration of the unknown, of the ion in the unknown sample. So basically, that's what you do when you're doing your calibration, and that's the purpose of the calibration, to help you determine, the concentration. Well, you know what the signal is. Now, I already mentioned that the performance indicators, or what I call the figures of merit, are all present, or you can actually extract them, from the calibration plot. And so the figures of merit that I'm talking about includes method specificity, linearity, accuracy, precision, range, and there are two types of ranges, dynamic range, linear range is often sort of the same thing, limits of detection, limits of quantification, and robustness. So this is what you call the figures of merit. And as you're gonna see, most often you can actually get them, from your calibration plot. So let me just define them very, very quickly. Method specificity, refers, to how selective your method is. Linearity, refers to is a signal increasing linearly with concentration, and by how much, So how wide is a range that you can go as far as the concentration is concerned to still get a linear signal response. The accuracy, I think we've talked about this before, that's the nearness to the truth. That's the nearness to the true value. Precision, on the other hand, it's how your data is being distributed around the mean. So you calculate it with the standard deviation. I'm going to show you shortly. The dynamic range, again, is a linear range, and I'm going to explain it shortly. And the limit of quantification, and the limit of detection, and so forth. So first, let's talk about accuracy. Like I've said, this is the nearness to the truth. And the truth, of course, is the true value. So how do you assess or demonstrate accuracy? How do you determine accuracy? And so you determine accuracy by running calibration checks. And calibration checks, just refers to taking one known standard solution and running it on the instrument. So you already know what it is. So run it on the instrument and see if you can determine its concentration, which you already know. So it's sort of a validation, type of thing. You can also demonstrate accuracy, by doing fortification recoveries that I'm going to talk about in the next slide. You can demonstrate accuracy, by running a standard reference material. Again, we've already talked about this. This is a standard that you buy from the manufacturer, and its concentration is very accurately known. You can also determine accuracy by running a blank. And remember, a blank, is a sample that doesn't have analyte in it. And so the signal of the blank ideally should be very close to zero. So if at all it's not zero, it means, we got a problem, and accuracy could be a problem. And precision, on the other hand, is referring to, running replicate measurements, and calculating the standard deviation. So I think I've already talked about this, the analytical blank. This is a sample that has got all the species present other than the analyte. So it doesn't have the analyte, but it's got all the other species in the sample present. Now, there are three types of analytical blanks, okay? So there's what they call the reagent blank. And this is a sample, that contains all components except the analyte. Often, you just mix all the reagents, that would be present in the sample, and you do the same, with the blank. Only that you do not include, the analyte. The method blank, on the other hand, is where you take the reagent blank and take it through all the analytical steps that you take the real sample through. Okay. And finally, the field blank, it's where you take, the method blank and even take it to the environment or to the field so that you can expose it to the same realities as what the sample was exposed to. I should mention this, that the field blank is almost impractical in a real life situation because it's difficult, to take the blank, to the field, and so forth. So in most cases, you're going to see in the lab, we're going to be using the reagent blank and the method blank. They are the most practical, to use in the lab. So I talked about fortification recovery, as a way to determine how accurate your analytical method is, the accuracy of an analytical method. So what is fortification recovery? And sometimes they call it spike recovery. Now, this is often very important if at all you are doing an extraction in an analytical method. All right. So maybe you're trying to analyze, say, caffeine in coffee. And first you need to extract the caffeine, from all the junk that is present in coffee, possibly using column chromatography or maybe using liquid chromatography. And so when you're doing that, you need to assess how good is your analytical method in doing the extraction. Okay. And so in this case, often you would take the sample and then you spike it with a known quantity of the analyte and then take it through, the extraction process, and then you do the detection. After you do the detection, you can actually calculate the percent recovery, which is calculated as follows, the concentration that you spiked minus, the concentration of the unspiked sample divided by the concentration, that you added, multiplied by 100, and that is what you call, the fortification recovery. Let me give you an example. Now, assume you get a situation like this. You get an ideal blank. And I've sort of explained to you an ideal blank, so this would be something like, a method blank. And you spike it with 10 parts per billion, of the analyte. Okay. A spike of 5 parts per billion is then added to a replicate portion of the unknown. Now, let me rephrase, the question here. So you got an unknown, and that unknown, it's got a known concentration, of 10 parts per billion of the analyte. And then a spike of 5 parts per billion, was added to this sample, that is known. Now, the analysis of the spike sample gives a concentration of 14.6 parts per billion. And so simplifying the percent spike recovery. I think you just need to substitute these. You've got the spiked sample. You've got the unspiked sample that you knew its concentration to be 10 parts per billion. And the amount that you added, is 5 parts per billion times 100. And you get, your fortification recovery. And you often need to have determined what is the acceptable recovery that you are looking for. In some cases, depending on the problem, you are looking for an recovery of more than 95%. And so if you get anything less than that, then it doesn't meet, the specifications. But nonetheless, that's how you determine the fortification recovery. Very important. So anytime you develop an analytical method and it involves extraction, you possibly really need, to do what they call the spike recovery, as I have shown you, in this simple relationship. Now, the other important figure of merit, is what they call the sensitivity. And the sensitivity means, the measure of an analytical method's ability to differentiate or discriminate between small differences in the analytical concentration, in the analyte concentration. Now, there are two types of sensitivities. And you're going to see that you can easily get them, from your calibration plot. So there's what they call the calibration sensitivity. And this refers to the slope, the M, the slope of your calibration plot. All right. So your slope, that's your intensity, that's the concentration of the analyte. And so your slope, which is M, is what you refer to as a calibration, sensitivity. The analytical sensitivity, on the other hand, is where you take the calibration sensitivity, the M, divided by the standard deviation of the measurement. So sometimes you do this so that you can account, for data distribution. So analytical sensitivity is often better way to quantify sensitivity because you are accounting, for the data distribution. And so you can see that the data distribution is concentration dependent. And so the analytical sensitivity is a better measure of sensitivity. But often, you find people reporting sensitivity just by looking, at the calibration sensitivity. So if at all you've got two methods and you're trying to assess their sensitivity, so you just need, to plot their calibrations, maybe method 1, method 1 and method 2. And assume that's the calibrations that you get for method 1 and method 2. So that means, the steeper analytical method, means that it's more sensitive. So method 1 is more sensitive, than method 2. So the bigger the M, the more sensitive, the analytical method. Now, the other figure of merit, is linearity. And linearity just measures, how your signal relates or linearly changes, to the concentration. Now, linearity is quantified very superficially using the so-called the regression coefficient or the square of correlation coefficient, which is determined, as such. Ideally, R squared, should be equals to 1. And so we are hoping, for a situation where the R squared is very, very close to 1. Now you're going to see, in certain types of areas, such as, biology and so on, they would often say R squared, of say 0.7, is fairly linear. However, in analytical chemistry, we don't consider it linear enough. So ideally, you're looking for R squared very, very close to 1. So dynamic range is the other figure of merit. And this refers to the range, again, at which your concentrations, gives a linear response. And ideally, you want a dynamic range, that is very, very large. So the dynamic range, refers to the limit of linearity, so that's the point at which your calibration deviates, from linearity. So that point at which, your calibration stops to be linear and starts to plateau off, so that's your numerator right there. And then the denominator is the so-called limit of detection, the limit of detection. So dynamic range is equals to limit of linearity divided by limit of detection. So how do you calculate the limit of detection? So the limit of detection is calculated, by this equation here. and you calculate it as follows. So the sigma of the blank plus 10 times the standard deviation of the blank. All right, so that's why you calculate the limit of quantification, in a quantitative sense. In a qualitative sense, the limit of quantification means the concentration at which your analytical method can reliably quantify. All right, so that's the lowest concentration that your analytical method can reliably, quantify. Now, on the other hand, the limit of detection, which you can see is very similar to the limit of quantification in terms of the quantitative calculation. So the only difference is, instead of 10, you've got a multiple of 3. And so qualitatively, the limit of detection refers to the lowest concentration that your analytical method can detect. So note the difference. So the limit of quantification, the lowest concentration that your analytical method can reliably quantify or reliably detect. Whereas the limit of detection is the smallest concentration, at which your analytical method can simply detect, but not reliably, meaning the standard deviation, is always very, very high. So take note of that, how you calculate the limit of detection and the limit of quantification. Take note of these two. The units, for limit of detection using this formula is signal units, because you can see the signal of the blank plus minus 3 times standard deviation of the blank, and this is the absolute standard deviation of the blank, which we already know has got the same unit, as those of the signal. And so the units here are signal units. In most cases, you are interested with concentration units, say parts per billion, parts per million, and so on. And so how do you get that? You just take the same equations here, signal units, and then you divide it by the calibration sensitivity. So the limit of detection in concentration units is equals to the signal of the blank plus 3 times standard deviation of the blank divided by the M, which is the calibration sensitivity. And same thing with limits of quantification. The only difference is that multiple of 10. Okay. So in the next lecture, we're gonna continue on the other remaining figures of merit, that we're gonna talk about.